Oh, good morning, good afternoon, or any time that you have a chance to watch this video. So we are seeing each other again through the video. So the schedule is really bad. All right. Sorry about that. So not good. All right. So we have the next handout that I would like to talk about. And because we are moving toward the last portion of the course. And I think, as we discussed in class, that I'm going to wrap things up and don't want to go too far and try to maintain the amount of material that is relevant to the final exam. So let's see what we have for you today. All right. So first thing first, I think you still remember this one. All right, so we're going to start with what we did in the previous lecture. We were trying to come up with the way that we can come up a way that we can find or determine the distribution function or distribution the density function of a function of a random variables. Okay, so what we got last time, we had two ways of doing it. We did through the probability calculation using the distribution function itself, or we have the second method that we used, the inverse transformation. All right, so that was the two ways that allow us to determine the distribution of a function of random variables. But then there's a third one, but this one I just want to talk about. I mean, it's not on passing, but I think this is something like an application of moment generating functions, because we knew that this moment generating function is really useful. It has so many things built into it in a very, very compact form. As you notice, this is exactly the formula sheet that you're going to get again in the final exam. But what we already learned about MGF, moments generating function, is like, for example, if you want to talk about the binomial distribution, you know the probability function, it's gonna look like this. You know the mean, you know the variance, but then the way that you can sort of like a package this whole thing into a very complex form is just like, hey, what is the MGF? And say, oh, okay, Ajan, MGF look like this, and you're done. And the uniqueness theorem of this MGF is stating that whenever you have a moments generating function that look like this, that's always going to be one to one, nothing else. It's always going to be the binomial distribution. Cool? All right, so that's why we kind of like, okay, that's kind of nice. So that means if you have a list of all of the shape and form of the moments generating function, what you have to do is just, comparing them, I would say, or recognizing. For example, if you can recognize, which of course, well, you have a table that you can come back here and take a look at, and any MGF that look like this will reflect geometric distribution, on and on and on, right? So you have the whole list of this whole thing. Here we go. You can have like a uniform, normal, exponential, gamma, chi-square. Everything is already listed here. All right. Even, I mean, more, of course, but we are going to stick with the well-known distributions on hands we have. Cool. All right. So we already learned about that. So what does it mean by the third method? All right. So we're going to look at the method of moments generating functions. I can actually give you like a spoiler alert over here, just saying that, hey, because we know already how useful the moment generating function is going to be. So let's take a look at this theorem one more time. So you say, let's m of sub x and m sub y denotes the MGF of random variable x and y respectively. Now, if both moments generating functions exist, we assume they must exist first, and somehow they are exactly the same, we say x and y must have the same probability distribution. All right, that's the uniqueness theorem of this whole MGF business here. Cool. All right, so with that, then it means if you have any function of this crazy, like we already named it u last time, so you can have like a combination of many random variables, okay, and somehow you try to figure out the moment generating function of this u random variable. So everyone still remember this for sure. Moment generating function is nothing more than just finding the expectation of the e to the tu. With me, guys? Okay, you still remember this. So it's just the expectation of an exponential of t times the random variable that you want to find, the mgf. So what you are trying to do over here is just evaluate this moment generating function. And of course, you can guess it at the end. If you come up with a form of the MGF that look like one of these, known distribution, bam, by uniqueness theorem, you know exactly what should be the distribution function of the U. Cool? Sounds nice? Yes? Okay, so that's what we're trying to get to. It's just like, hey, the business is just going back to evaluating or determining the MGF function. But the additional steps that you have to add on top is just recognizing the final function that you already obtained. Does it match any one of the known MGF? So, I mean, there is some limitation in this case. Of course, Wajan, what if I calculate the MGF and then it doesn't really match? I mean, it doesn't look like one of those, MGF in the table. So, too bad. So maybe this is like well, yeah, the negative side of this one. If it doesn't fit one of those, then you probably have to go back and use one of the other two methods that we studied last time. All right, but anyway, all in all, most of the time you will end up with one of the known distribution anyway, because you are not trying to do something so exotic that no one has seen this kind of distribution before, or this kind of distribution, I mean, kind of not well known, because, well, it must be super weird if you come up with something different that no one has used it before, right? That is sort of doesn't make sense. All right, okay, so let's take a look at this one. This is going to be very familiar to you. So suppose that you have y is normally distributed. Cool. All right. And you already know that this y has the mean mu and the variance sigma square. So the asking question is, if you come up with the z variables, and whenever you look at the z variable, you already know this is a standard normal distribution. You have used this since, I don't know, high school statistics. It's just the y, you subtracting the mean divided by the SD. This is what I'm saying. You already created a function of y. All right. And now the new function that you generated is called z. All right. They say, what is this distribution? What is the distribution of z? All right. Without proving it, you guys know already. But you're going to end up with the normal distribution anyway. However, once you learn, when you study the z, you know that, hey, if you talk about this z, then you already know that the mean will be at 0. Yeah, and the variance is going to be 1 because you standardize this whole thing. How to prove it, though, right? Remember that? So, I mean, not remember, but I mean, it's just like saying that, hey, all right, I know that y is normal. You already, this is sort of like automatic, that z must be normal as well. But now it's the time that this is the way that you can prove it. The way to do it is this. All right, don't worry. When you look down in this handout, you look like, oh my God, it's going to be a lot of trouble. If you really want to dig deep, yes. But if you just want to watch this one on passing, it's not that bad. All right, take a look at this. So what you want is you just want to evaluate the moment generating function, yes, of that z, okay? So what you have to do is you just try to find the expectation of e to the t times the function that you are looking at. But then the trick that this textbook is using is just they want to start with the g, which get rid of the sigma, and then they're just going to throw in the sigma later. That can be done as well. All right, so let's stick with the textbook the way that they did. So what is the expectation of g, which is just y minus mu? So it's just an expectation of e to the tg, and it's just replacing the g, the function of y, as a y minus mu. And then now it's time for you to evaluate this expectation. but it's still simple expectation of whatever. You just plug whatever in there, followed by the whole PDF, which is normal. All right. And this is the one that you're probably going to hit a lot because the normal function itself looks pretty bad. It's an exponential of this whole thing divided by 2 sigma square. And there is a factor underneath the whole exponential, which is sigma square root 2 pi. All right. It just, the normal function itself is kind of bad. All right. Here comes the question. How can we evaluate this integral? Uh-oh. All right. So this is the whole thing. If you can evaluate this, your business is almost done. Once you're done with the evaluation or determining of this moment generating function, you just go back, compare with one of these if it fits, and we hope that it's going to fit this form. Look at this. This is the moment generating function of normal distribution. So eventually, if you come down to this, then your life is good. All right. So, well, we're not going to do that. I used to teach this, and it's like we spend like 15-20 minutes try to show you how to evaluate this integral. But at this point, I don't think you need it. It's bad in the sense that is the integral that all you have to do is just manipulating the variables, make it like a complete square, rearrange the term, doing the substitution techniques a little bit. All right, I can quote the end. It turns out, okay, that moment generating function look like this already. It looks pretty good. All right. After the integral, it looks like that e to the t square is back. See? You get e to the t square with divided by 2, and you have a sigma square. It has the form that looks almost pretty close to the, to the one that we had here. Yeah, almost. It's e to the t something something sigma square divided by 2. So it's kind of nice. All right. So what you have next for you to do is, hey, I'm done. I already learned about the expected of g, which is just y minus mu. You can turn this into z simply by you want to, here, introduce that sigma underneath, which is fine. So it's just like you try to replace the t with the t over sigma. Think of it that way. All right, because t is just sort of like the parameter that you introduce during the MGF calculation anyway. So you can pretty much like change of the variable. Let's rename the t to be t over sigma. All right, so that means whatever you got back in the day, you can actually replace the t with the t over sigma. And then you still got everything looks nice and tidy. This is it. See? So it's the other way that you can look at this is just like you wrap this t over sigma to be the new t. Think of it that way. All right. So with that, that means your final form of the MGF for the standardized normal random variable, the z, the standard normal z that you defined earlier, give you this moment generating function. All right. That's it. That's my conclusion. All right. Forget about those integral crazy stuff. Don't worry about it. Let's say that you already tried to find out the moment generating function of z. And this is your final step, is e to the t square over 2. Can you conclude now what is going to be the the distribution of z? That's nice. Look up in the table, comparing with this form, which is the MGF of a normal distribution. Hey, Jan, that's kind of cool. Because when you look at this, they are the same except you pick mu to be 0. So this first term is gone. And then you pick sigma to be 1. So this thing will be gone as well. So this disappear, that turns into 1, and everything will give you back this e to the t square over 2. And that's it. In conclusion, you can draw, the c must be normal as well, with the mean to be 0 and the standard deviation or the variance to be 1. And you are pretty much done. Cool? All right. So that's what I'm trying to say. And for this method, I think the technical difficulties turns out to be just evaluating the MGF. That's pretty much it. All right. Once you're done with that, the extra step is trying to compare or trying to recognize the final form of the MGF that you obtained. And if you can find one of the form to be exactly the same as the one that already known by uniqueness theorem, is one-to-one mapping. So that means it's guaranteed that the distribution has to be the one that matches the MGF obtains. You're done. Okay. All right. So just don't want to put material too heavy. This one, I don't think I'm gonna ask you this in the exam, because as you can see, technicality it's not in the method. The method is simple. It's comparison or recognizing the form of the MGF. But the technicality of this one is more like how can you figure out the MGF, which, well, we already had that in the midterm questions, asking you to find out what is the MGF of this of that. So to me, it's the same purpose. All right. But this method is just utilizing the uniqueness theorem of the moment generating function. Sounds cool? All right. But anyway, I have one more example. As we say, we don't want to worry too much about the integral, but the consequence or the result of this one is so good. Look at this next example right here. So if you have z to be normally distributed, okay, with the mean 0 and variance 1, so it means you sort of like top up from what you already did. You already knew that the z is a standard normal. Now, I'm building another function on top of the z. Well, hey, I want z square. You do that all the time, right? The reason that every time you have to do the square is when you want to calculate the variance, for example. You want to find the expected of x squared, you want to find expected of y squared, on and on. So it's the same thing. You want to find the expectation of the square function. So here comes the questions. What is the distribution of z squared? Can you guess? All right. I don't know. Can you guess or not? Depending on the previous statistics course. But the idea is if you want to follow the moment generating function method, all you have to do is step by step. Well, Ajahn, don't have to do too much. I want to find the moment generating function of z squared. All you have to do is just put the z squared on top of that exponential t. Then whatever the exponential function is, whatever the function that you want to find expectation, just plug this whole thing in here, followed by the PDF, the probability density function. And because probability density function that you got right here is already just a standard normal, so standard normal look like this, which is fine. Okay, right there. E to the tz squared is in the front. Now, as you can see, the main task is finding out this integral. Question is, have you done this before? So the problem is, this is not good. This is the function that you cannot use just a regular method that you learned from maybe calculus 1 or 2 to evaluate, because you have a z square function in the arguments of the exponential. You don't have any formula of this. You only know how to maybe integrate the exponential function, but not the exponential of some variable square. That doesn't work. All right. So don't worry about it. We're not going to try to do this. I think the trick that we use to evaluate this one, I mean, not used to, but I mean, we usually do it, is by using the polar coordinates or something like that. All right. So we have to, a lot of stuff that we can throw away and throw around, try to evaluate this. But anyway, let's say that assuming that you know how, and let me quote the form of the final result. Here, guys, look like this. All right, let me highlight this one. So let's say at the end, this is what you get from that integral. See, the way that I'm going to do is just recognizing this. Can you recognize this MGF? Oh, John, it pretty much like the gamma, the MGF of gamma. Not only that, now once you see that, hey, gamma has this MGF form, now you can pinpoint or determine right away what should be the alpha and what should be the beta for the gamma. Is that cool? Isn't that nice? So once you have that, that means it's done. So you can conclude right away the z square must be gamma distributed with the alpha equal to 1/2 and beta equal to 2. And we already had the name for this. Okay, every time that you have this, then you call it, hey, it's a chi-square distribution. All right, because the chi-square distribution is when you have the beta is equal to 2 and the alpha 1/2, saying that, hey, the degree of freedom is 1. So in conclusion, this probably coincide with what you have already learned before. If you have z to be normally distributed random variable, the z square will be chi-square distributed. And that's it. You are done. Nice. All right. But at least I know now that you have a way to prove it, or at least you have a way that you can connect going from z to z square. You're going from standardized normal distribution to a chi-square distribution this way. All right, using the method of moments generating function. Cool. I think it's kind of cool. Yeah. All right, guys. So that's it. So with that, the method of moments generating function is often very useful for finding the distribution of the sum of independent random variable. The reason that, I mean, of course, I said we're not going to ask you this in the exam. And I don't think we're going to have you do this to prove things. But the nice thing about this one is, I think we already at a point where you understand why we love the independent random variable so much, and why we love to conclude that every time that you have things that are independently distributed or related, their functions, their MGF, their PDF, their, I don't know, probability calculation, whatever, can be put in a product form, right? We already concluded that, right? So this is going to be the same thing. So if you try to come up with a sum of random variable like y1 plus y2 all the way to yn, then it turns out the moments generating function of those sum can be put in a product form. Nice. This is good. All right. This one you can prove it easily, but the easiest way that, well, you can think about this is just, I mean, the proof is actually pretty quick, because all you have to do is just finding out the moments generating function of u, but the u is simply just the sum of all the y's. But you know that the exponential with the arguments in the summation form can be put in a product form, right? You split each term into each exponential that is multiplying. And now, because each term in this exponential form are independent of each other, from the independency that we learned before, you can split them into each individual integral. So that means you can extract the calculation for y1, followed by the y2, all the way to yn. Do it one by one separately in sequence or whatever order that you want to do. But at the end, is just going to give you a product. And now each one, of course, going to give you back the MGF of y1, MGF of y2, MGF of yn. So no doubts. Yes, the moment generating function of the sum is going to be equal to just the product of the MGF of each individual variable inside that summation. Done. Cool. All right. So this is once again still within, you know, the area that we can conclude pretty easily that, hey, products is nice because it's kind of like a result of independencies. Yeah, always love it. All right. So let's take a look at this. And I hope this will clear things up one more time. All right. So if you have y1 all the way to y sub n are independent random variables, and let's say each of them are exponential distributed. All right. Cool. Like this. All right. Now, let's say that to make it a little bit more realistic, let's y1 denotes the time until the first arrival. Y2 denotes the time between the first and the second. Y3 is going to be the time between the second and the third, on and on and on. So now y representing the time between arrivals. Okay, so this is pretty realistic because what we did back in the day of remember when we study exponential function, we said if you try to model the arrival times of maybe customer in front of a convenience store or arrival of a car at toll booths and on, those are exponentially distributed. So this is exactly what we want, right? So we sort of like we used this before, but then it turns out, well, hey, John, if I want to know what is going to be the whole wait time, the time that you have to wait for the whole thing being done. So as you can see, because you have to wait until the last arrival, that's the complete of the whole process, and that is the whole waiting time. All right, from the opening of the counter until the end customer arrives. So this means you just have to wait for y1, y2, y3, y4, all the way to y sub n, and then you have to add all those interval of times together. So this is your u. Your new variables is just the sum of those interval of times, y1 all the way to yn. Does that make sense, right? Just like the total wait time is going to be the sum. But then because each individual terms of those are just going to be exponential function, and you can just use this theorem right away, Bajan. Oh, whoa, nice. If you just know that your u is just a summation right here, you know that now your moment generating function is going to be just the product of each y. Okay, cool. But then because you said everything distributes with the same distribution, they look exactly the same. They're sharing the same theta. I mean, the same parameter for the exponential distribution. So that means each term look exactly the same because it came from the same distribution. But the only thing now that extended the whole thing is just now you want the product of n terms of this. So all you have extra is just that n times. I mean, you multiply with n times. So you have the nth power of 1 minus theta t, the whole to the negative n. What is this distribution, guys? Yes. Go back and take a look at the table of MGF. All right, so that's it. Once again, it's 1 minus theta t all the way to the negative n. I mean, you don't have to look so far. It's right here. 1 minus something t to the negative thing. That's once again gamma. So that's it. So it's a gamma distributed with alpha to be n now, and the beta is the theta, the same parameter that shows up inside the exponential function. All right, and that's it. You are done. Cool. All right, but I mean, you already knew that the exponential distribution is part of, or is one type of the gamma distribution, right? But then now you see the connections. So when you have the exponential function, but then you want to build the summation of all those exponential functions, it turns out you elevate. Well, it's not elevation or anything, but I mean, you ends up with a different type of distribution, even though it's the same family anyway, but you turn exponential function into a gamma. Yeah, that's kind of nice. Cool. All right, that's neat. All right, so this is going to be extra theorem that allow you to extend not only just a pure summation, but now you can do the linear combination of those y's. So that means if u has a little bit more complicated form, but it's still linear summation anyway, so you allow to have some coefficients in front of each y. So it's going to be a1 y1 plus a2 y2 all the way to a n yn. Then by using the same trick and thing, all right, you know that you can find the expected value of u, no problem, and the variance of u use the same trick as what you did before. Okay, so the expectation is simple. It's a linear combinations of all those mu anyway. And then for the variance, don't forget to square the coefficients in the front, and you follow by the variance of each individual y. Okay, so this one is no big deal. All right, but then what you have next is now this is a conclusion that we got. So if now you have y sub y1 all the way to yn, and now we already understood that if you built a standard z, okay, and then you take the z to square them, right? So now we already know as well that the z square is gamma distribution, right? I'm sorry, the chi-square distribution. And conclusion that we have here is the sum of those still chi-square anyway, but with the n degree of freedom. So if you go back here, okay, so right here, so when you only do one of the z, you have only one z square, you get to the chi-square distribution, but the degree of freedom is just only one because you only have one of the y. But now up here, you get a little bit of extension because now you have more than one. You have y1, y2, y3, y4. But then you already knew that each z square will be chi-square. But now the sum of those, so you have a lot of that chi-square. But now you think in your head, well, all right, so because chi-square is a gamma anyway. All right, so once you combine those, multiply the MGF of each chi-square, at the end you still get the chi-square because the beta does not change. The beta stays the same. I mean, I'm not trying to, here we go. All right, here. The beta in here stays the same, but the only thing that's gonna get powered up is the alpha. So that's why the degree of freedom is gonna get extended. Instead of you get 1/2, you're gonna get n over 2, and that means the degree of freedom is gonna be n instead of 1. There you go. Cool? All right, so I hope by showing you this method of moment generating functions, I think it's kind of like nice and tidy in the sense that, hey, it's not only now already knew that MGF is very compact, easy to use, and it's unique to one-to-one to the distribution function. Now you can utilize this, as a tool to determine what type of distribution is going to be utilizing that uniqueness theorem. And once you apply that to a known functions here, for example, normal distribution or exponential distribution, then it's an easy way that you can prove or verify what should be the distribution of the new function that you generated. Cool? All right, so I hope you see what I'm trying to say. I think maybe two things that you can make the connections over here is, all right, let's go back. You have just a regular normal. You standard normal, the z, okay? You can prove that using the MGF method. You take the z, which is now you proven to be normal. You square that, you showed, or I mean, the theory and everything showed that is chi-square. All right, so it's kind of like come nicely like this. And if you only have a single z square, it's going to be the chi-square distributed with 1 degree of freedom. And then this method extend you to even the sum of the z square, showing that it's still chi-square, but with the n degree of freedom, right? That's one big example, the whole train of thought. Another example is if you have an exponential function, okay, right here, and you have some of those exponential function by doing this method of moments generating function, you just proved that at the end you get a gamma distribution. Yeah, so it's kind of nice. Okay, so I hope this works. So in summary, the summary is simple now. Let u be a function of random variables y sub n all the way to y sub 1 all the way to y sub n. Of course, the main task is find the moment generating function for u. This is the most technical part, right, which we're not going to try to do here. And then second step is compare. All right, yeah, just compare, look it up or whatever to other well-known. We hope it's going to be well-known. All right, once you found it, bam, by uniqueness theorem, it must be that distribution. All right, so this conclude the third method of finding out the random distribution function of a function of random variable. Is that confusing? So this sum up the third method of finding out the distribution function of a function of random variables. Okay, so I hope you not get confused. All right, cool. All right, so I think that's wrap up this chapter right here. All right, but I mean, talk about if you would like to talk about the question in the exam, I think we're gonna stick with the first two methods. All right, because this method, as I said, I'm not gonna try to have you calculate like a super complicated integral and compare the formula because I mean looks pretty bad. Already cool. All right. All right. So next, we already done with the chapter here. I hope this sound effect doesn't really disturb you that much. All right. So now we're going to look at something that's, I think this is going to be the part that's kind of like cool things down because this is going to be the part where you already familiar a lot. All right. So I think this portion of the chapter 7 in this handout is going to be the part that I think you have done this so many times. So the nice thing about this one is going to worth one problem in the exam, right? And I'm trying to make this thing easy for you. So stick around and just follow me. I'm not trying to go too far, so don't worry about it. Even though there is a reference in the handout that go beyond just like a go all the way to like T distribution, F distribution. We're not gonna do that. All right, we're gonna stick with the something that we already understand pretty well, the normal distribution, some simple exponential distribution, and we call it done because we would love for you to just understand the mathematical methods that being used in statistics. All right, not trying to present you with the difficulties of mathematics in statistics or something like that. I hope that's something that's kind of nice. Okay, so let's come back here. All right, so let's do like a quick recap according to the textbook here. We say that in the previous chapter, we represent the methods, right, of finding out the distribution of functions of random variables, right? We have 3 methods introduced already. Okay, so what we kind of like learn from there is the random variables y1 all the way to yn are independent. We love that. We still stick with that. All right, and have the same distribution if we draw things from the population of interest having the same distribution. Okay, so that means you observe all the y's selected from a single population of interest. You're not trying to do anything like cross population or anything, so it's kind of nice. So the good thing about this one is, right, a certain function of random variables observed in the sample are gonna be used to estimate or make decisions about the unknown population's parameters. And that is the whole thing about the sampling distributions and the sampling business. All right, it's because in reality, you cannot just go out and collect all the information of your population. It's maybe too big. You cannot do it. So the way that you can do it, you do the sample, right? You maybe go out, pull some sample, and then do the data on that sample, and you're trying to do the estimates. So that's the whole business here that we want to do. Either make estimates or making decisions, all right, based on that amount of data or amount of information that you gain. All right, for example, let's look at a quick example right here. And this is going to be exactly the same as what you have done before. Suppose that we want to estimate a population mean. This is a very common estimation. And if we obtain a random sample, all right, we still stick with the random sampling method, right? Because that's the unbiased way of doing the sampling method. And let's say you do that in observations. So you do it, you know, the sampling 1, sample number 2, you do another sampling again, you have sample number 3, all the way to n samples. So you have n observations there. And it seems reasonable to estimate the mean of the population, which is that mu right here. We use the Greek letter to representing the population's parameter. With the sample mean, right? You use this. We use this since high school statistics. Okay. So here comes the question. How good is this? How good is the y bar is going to be used to estimate the mean of the population mu? Okay. So the way that you can answer the question about the goodness, how good is this? depending on the behavior of the y bar itself. With me? The reason I say it has to depending on the behavior of the y bar, because now y bar itself is a random variable, even though it's not a function of variables, but itself is another variable that is random. So that means the y bar itself will have distribution. So you will be able to tell how good is using the y bar to be the estimator is depending on the distribution of the y bar itself. Okay? So the effect that this behavior has on the y bar is you have to know the distribution. That's why we learn 3 methods of finding out what is the distribution of function of variables. Okay. All right. But anyway, the point that we want to make here is we call this a statistic. Right? We want to use this as something, as a statistic, something that you want to infer back to the population. All right. So in conclusion, the definition of statistic is a function of observable random variables in a sample and known constants. You want to use this to be your statistic. Okay. All right. So the statistics are used to make inferences, right? Either estimates, decisions about unknown population parameter. Okay. Because all statistics are function of random variables observed in a sample. So the statistics itself are random variables. This is the key. And I think this is the part that I keep emphasizing all the time. And I think this is the annoying part, because it's sort of like there are so many layers of randomness. Everything are random pretty much. Consequently, all statistics have probability distributions that we're going to call this the sampling distributions. All right. So this is the part that is going to provide a model, which is a theoretical model that's gonna give you some distribution, and then you're gonna use this to sort of like do the estimation and everything. Okay. All right. So, well, I don't know I'm gonna talk too much on this or not, but I think the reason I include this paragraph over here is from a practical point of view. Okay, the sampling distribution of a statistic provides a model, right, of frequency histogram of the possible values of the statistic. That if you want this histogram, you have to repeat the sampling, which in reality, you're not going to do this, but you're going to use this theory to assume that it works. And you're just going to do it. Do it mean collect the data, do the sampling, do the questionnaire and everything. Once you get the data, once you get some information there, and then you follow the statistical methods and you do the inference estimations, making decisions based on the theory that you learned over here. So the key that I want to add here is just you have to do the repeated. For you to be able to get histogram, you have to do it over and over and over for you to be able to build the histogram out. All right, so I hope this helps. Or maybe if it's too confusing, just forget about this paragraph over here. All right, so the easiest way is just taking a look at one example. It's going to be simple. All right, so you have a die which is balanced and is tossed 3 times. Okay, let's y1 all the way to y3 denotes the number of spots observed on the upper face of the torus. So มันออกหน้าอะไรเอาอันนั้นเนาะ All right, suppose we are estimated in the y bar. We just want to get an average numbers of spots that those 3 torses will give. So what are the mean and the standard deviation, okay, of the y bar? That function we just generated is just the sum of the 3 divided by 3. And how can we find the sampling distribution of y bar? Cool. All right, so let's take a look at this. It's going to be straightforward because the y bar is just a linear combination of all the 3. The same coefficients is just 1/3. So it's just y1 over 3 plus y2 over 3 plus y3 over 3. So no problem. It's just the coefficients multiplied by the mean. Okay, that's no big deal. And what you have over here is because you know that each one comes from the same mean. So that's why you can replace this with the mu sub I, same numbers, mu. Let's call it the sharing the same average. Okay, this same mean. Okay, so with that, then mu can be pulled out from the integral. Not integral. Sorry, can be pulled out from the summation. And because the coefficient is simply just 1/3, or in this case, it's just you can put any n into it. It doesn't have to be 3. But anyway, at the end, those summation and 1/n will cancel out. So you get the mean mu back. That's it. It's going to be 3.5. Okay, so the number of spots go from 1, 2, 3, 4, 5, and 6. Okay, so the mean is going to be 3.5. All right, so this is good. So that's the expectation of the y bar. Now, if you want to find the variance, so it's still no big deal because the variance is simply you take the coefficient square and followed by the variance of each of the y. Okay? So what you have over here is, all right, once again, you're sharing the same variance. So I can replace all the sigma sub I to be just the same sigma. So the sigma square, once again, can be pulled out. 1/n square can be pulled out. The sigma square, you just have to add n terms. So at the end, you're going to have n on top, n square in the bottom, cancel one of them. So you end up with the sigma square over n. Okay. But then if you do the punching, the calculation of the variance of each sample, so what you're going to get is you're going to get 2.9167. So this one is just, you're doing the same thing as you did before. This one is just like they find the expected of x, of y, sorry, in this case, square, and subtracting out the expected of y, the whole thing square. All right, so you just take the mean 3.5, and then you take 1/3.5. Subtracting 1 away from 3.5, 2 away from 3.5, on and on. You try to calculate the variance of each sample. But then it turns out the variance of the y bar is that variance, but then divided by 3. Okay, that's good. All right, so that's it. The way that you can, come up with the distribution of y bar is simply just doing the calculation that you usually do with the function of variables. All right, that's no big deal. Now, but at this point, what you're doing over here is just finding the mean and find the variance. How can we derive the distribution of the random variable y by itself? Okay, now, so the possible values of the random variable is going to be, right, 3, 4, 5, all the way, right? Because you're going to have to sum all those numbers. So that means if I list all the value of the W, you're going to start from 3 because that's the lowest possible number of spots. It's like 111, okay? And the biggest number is going to be 18. 666. So it's going to be 18, all right? And you can generate the y bar simply by taking the W divided by 3 because it's exactly the same as the sum divided by 3. And now what you can see is you have, crazy amount of, it's 6 times 6 times 6. So there are 6 cubed ways that you can come up with this combination of all the spots that come out. So what you have over here is you actually have to plot that out. And you see the distribution of these numbers pretty easily. But it's a lot of work, but it's doable. So you just have to look at the frequency, right? So it's like, hey, how many possibility that you're going to get 111 or 3? Then you say, oh, then it's only 1 out of 216. So that's 1. And then you move on. What should be the probability that the W is 4? W is, don't forget, it's just a sum of all the sum of all the spots. And then you keep going. What is going to be the probability that the W is 4, 5, 6, 7, 8, 9, all the way to 18. Okay. So from there, then you will be able to sort of like get a histogram. Okay. So that is, in theory, that is going to be the case. If you repeat this experiment forever. Right. That's right? We talked about this since the beginning of the whole course. It's just like that's the concept of probability. The reason that each phase of the die come up in an unbiased die is going to be 1 over 6 ความน่าจะเป็นเท่ากัน1 ใน 6 1 ใน 6 How can you know 1 over 6 You have to repeat that dice tossing like infinitely many times, and you will see that each phase that shows up has the same probability 1 over 6 1 over 6 1 over 6. So the same idea over here. The calculation that you do here, or the probability determination that you're doing over here, you assume that the observation is being done, forever. All right. But that is a theoretical limit, pretty much. That's the way it's supposed to go. So look at this sort of like a real experiment. You do that, bro, 4,000 times. See, the distribution is going to be pretty close. Yeah. But if you do it only one time, you're not going to know what kind of distribution is going to be. But if you repeat this many, many times, the shape of the distribution will reflect what you expect theoretically. All right. So I hope this doesn't take you too far off, but I hope by showing you this kind of thing, give you like an idea or the connections of why we were trying to do the distribution of a function of variables, because this is the applications right here. Okay, I hope it helps. All right, so let's conclude in terms of theorem over here. All right, so what we can say, or at least what we can learn from here, is if you want to apply to a normal distribution, because this is the one that we pretty much like familiar the most. So look at the theorem 7.1 and see if you kind of like relate to example that we just looked at. Let y1 all the way to yn be a random sample of size n from a normal distribution with the mean mu and the variance sigma square. Then the y bar, a well-known y bar, is also normally distributed with the mean here, all right, with the mean of the sample to be exactly the same as the mean of the population. However, the variance of the sample, okay, will be the variance of the population over the number of sample that you draw, sigma squared over n. We got this result from this example right here. You can see that now by building up the summation of random variables, linear summation, right? A1 y1 plus A2 y2 all the way to an yn. The variance of that mean has a factor of n underneath. So what it's saying over here is the bigger the number of samples, the smaller the variance, which makes perfect sense to us, right? We kind of know if you increase the number of samples, right, then your result will be more accurate. That's sort of like now it's come in like your nature of thinking. That's the way it is. But at least now we have some sort of like a mathematical expression for that, right? We got that factor of n underneath due to this, the variance calculation of a linear combination of all those random variables. Okay, all right, we know that. All right, so that works right here as well. Okay, so that's what we're trying to get to, saying that, hey, if you do the random sample and you try to find the variance of that sample, okay, it will get better with the bigger n. And of course, I don't know if this helps, but imagine that if you take n to be, well, let's call it infinity, super big, then the variance go to 0, right? What does it mean? Of course, well, when infinity doesn't make sense, right? But at least when you say n is super big, the standard deviation of the sample will go to super small value. What does it mean? It means eventually, if you do the sampling so many times, eventually you're going to calculating the variance of the sample itself. Damn. Done. All right. With perfect accuracy, no standard deviation, no variance whatsoever. It's guaranteed for you to get back to the sigma square, something like that. All right, that's kind of nice. All right, so that's it. I don't think I want to dig too deep on this. All right, and I hope by showing you this, I think this is going to be the main example that I want you to just study this and put like a 3 stars onto this. If you understand this one, I think I'm done, because this is just like iteration of what you have been doing so many years in the past. Look at this. You have a bottling machines that can be regulated so that it discharges an average of mu ounces per bottle. Right. So this one is like a big machine doing this all the time. It's been observed that the amount of fuel dispensed by the machine is normally distributed with the sigma. So you know the sigma is already given from the statistics collected long time ago. So it's 1 ounce. So think of it like a plus minus and stuff. So a sample of 9 filled bottle is randomly selected from the outputs of the machine on a given day. So you're doing a quality control once again. And the ounces of fill are measured for each. So you check 9 bottles and see how much is going to be off from the average. Find the probability that the sample mean will be within 0.3 ounce of the true means for a chosen machine setting. Do you get that one, right? So, of course, because you do the 9 fills bottle, so that is a number of sample that you take in, okay? And you want to know how, if you take that 9, try to calculate the mean of that, how far away, with some probability, of course, will the mean be within 0.3 ounce of the true means, right? What is the probability that your QC sample will have the value of the mean further away from 0.3 ounces? That's the whole business here. Okay, so what you have here is, the Y bar is just the sample mean, and we kind of know that it's going to match the actual mean of the population. But because the variance of the Y bar is the variance of the population over N. So now you know it's going to be 1/9. That's your expectation, right? From theory at least, right? So with that, it means you want to know what is the probability it is stay within 0.3 ounce of the true mean. So what you're trying to calculate is what is the probability that the Y bar, the mean of your sample, away from the true mean, the mu, is going to be within 0.3. Yeah. So that's, you already put an inequality over here. So you can spread this thing out and write it out as the Y bar minus mu to be between negative 0.3 to positive 0.3. But then I can standardize this by divided through by this standard deviation of the sample itself. So that means I divided by sigma square over N with the square roots. I divided by SD alone. So let me put like SD over here. It's going to be sigma over root N. So I divide through by sigma over root N. Okay, no problem. So the reason I'm doing that, because here, this is my standard normal. I know that, right? Because I pull one from normal distributions. We already learned that the function of y minus mu over some constant over here would give my normal distribution. Perfect. So with that, it means I can now use the Z standard normal table. You can look, given in the exam paper, look it up, and you just want to take a look at where the Z is going to be when the value runs between minus 0.9 all the way to positive 0.9. All right, just use the table. You can evaluate the probability. So what it says is you have about 63% chance that your mean is going to fall within 0.3 ounce of the true mean. Is it good? All right, so it's not too bad. All right, so this lead you to a way that you can, do some, now you can expect that the next topic will be about estimation, right? You can estimate, or level of confidence. How much confidence are you? Oh, okay, I am about 63%. I'm pretty confident. With the 63% confidence, level, speak roughly, that my the mean that I got from the sample is going to be within zero point 0.3 from the true mean, something like that. All right, so that's natural. All right, what about asking in reverse? Well, hey, if I want to be able to, okay, observe the sample until my y bar going to stay within 0.3 ounce. So the question is now backward. How many observations should I use for me to guarantee, or don't use the word guarantee, for the y bar to be within 0.3 ounce with the probability of 0.95? So I want like 95% level of confidence that I want to be 95% sure that the y bar of the sample that I take is gonna fall within 0.3 ounce of the true mean. Yeah. Now, question is reverse. I'm asking of how many samples should I pick from the factory. All right. But anyway, the concept stay the same. So what you want is, of course, the condition is y bar must be about y bar must be at 0.3 away from the mean. So I can re-express this as usual. All right. But then what you want is you want this probability to be at 0.95. And you do the same way of standardizing this whole thing. You can divide on the inequality here with the standard deviation of the sample. You standardize everything into the z. So what you can see that, hey, you just have to figure out these two values here, the left and the right, that will give you the probability of 0.95. Done. Cool. And once again, use the normal distribution table. You know that, hey, for me to get 0.95 probability, these two numbers has to be at 1.96. And from here, I can reverse calculating what should be the n. So I'm saying if you want to be 95% confident that this whole thing is within 0.3 ounce, pick 43. Then it's 0.2 something. So pick 43 bottles from the factory to do the QC. Cool? All right. So I think this is enough for you to be able to connect between what does it mean by sampling process and the sampling distribution. That's going to get you connected to the population parameters. Okay? All right. That's kind of nice. So let's do the next one here. So once you understand, or you can connect between why we had to know how to find out the distribution of a function of variables, this is what it is. I can conclude from what we just learned earlier. Look at this theorem. If y1, y2 all the way to yn is defined as in the previous theorem, which is normal distribution and everything on and on, then look at this. Z, okay, no problem. You build Z, standard normal, okay, and assume that each Z, of course, is going to stay independent, all right? And now you love to do this. Sorry. Z squared. Woohoo. All right. So you start from the Y, you standardize it, turn it into Z, but then you not only want the sum of the Z, you want sum of the Z squared. And this is a nice thing that we just learned from the previous methods of moments generating function. It's right here. See? So the thing that's kind of nice now, you already learned that the sum of the Z square has the distribution of the chi square with the n degree of freedom. So we can use that results right here, right away. And your life is good. See? It's going to be chi square with the n degree of freedom. Love it. All right. So as I said, it turns out the difficulties has already passed. As long as you don't want to prove them. You just use the results. And look at the next exercise. It's going to be straightforward. You have Z1 all the way to Z6. Denote a random sample from standard normal. Love it. What is the probability that the sum of the Z square is less than or equal to some number B? To be equal to 0.95. See this? So now you took the knowledge that you already learned. That, oh, then I know that the Z square must be chi square. And because you have number of sample to be 6, so that is going to be the degree of freedom of that chi-square distribution as well. So the only thing left for you is, once again, refer to the table, but now it's going to be a different kind of table. This is going to be the chi-square instead. That's all. All right, but nowadays you probably use computer. All right, but anyway, stick with the classic textbook style. So you just open up the the chi-square table and look it up. So because this, when you refer to the table, you have to look at what does it mean as well. In this case, the chi-square in the textbook, they refer to the alpha to be the area on the right side. Okay, so it's mean, all right, that's going to kind of know. So because you kind of want to calculate the probability when this sum of the square z to be less than b has the probability of 0.95. That is the area over here, 0.95, right? Less than or equal to. However, because this table quoted the area beyond or to the right of the value right there. So that's why you have to look for the table when the alpha is 0.05, which is right here. With me? All right, so you are looking at this column right here. All right, and when you already see this column right here, now you try to find the place where, look at the degree of freedom here. Bam, 6. So that's it. So you look at the intersection between these two rows, that leads you to this number. So at the 6th degree of freedom and at the level, or not the level, let's say at the probability that the alpha is 0.05, the value that give you this is 12.5916. So that's it. So that means that is going to be the value that you want to evaluate right here. With me? That's the B, that is the one that you want to evaluate. So what it say is the probability of the sum of the z square when it's greater than that number, 12.59, it will give you the probability of 0.05. That's it. So that means the B that you look for, it's this number right here. Done. All right. So speak in terms of the quantile or the percentile. You can see that the B equal to 12.95 is the 95 percentile or 0.95 quantile, if you want to speak between 0 and 1. Okay, but I mean, don't worry about the terminologies over here. I think you understand in terms of the probability. I think that's already good, right? Once you know how to identify that the area that this inequality was talking about is the one in the white, 0.95, and this table referring to the alpha as the shaded area on the right, I think you're good. Cool. All right. So I hope this kind of like give you an idea, and I'm gonna just leave you with this in the sense, when I say leave, it's because we don't want to prove this one. But if the chi-square distribution plays a very important role, because this is the one that you're gonna face a lot. For example, if you look at this formula, of course, but then this is the one that we use to evaluate the the variance, yeah, of the sample. So it means you just have to take the y sub I and you subtract it out with the y bar. But then you have to square it. This is the reason why you have to deal with the chi-square function, because you have to square. Okay, and if you want to standardize this one, is definitely you're going to give you the square terms of the z, and that's going to be chi-square anyway. But then there is one more thing that we want to add on top of this. It turns out, suppose that we wish to make an inference about the population variance, okay, based on this. So what we just did before was just trying to infer to the mean, okay, the mean. But now, but what about I want to infer to the population variance? What will be the estimator of that? Because from what we have seen, the y bar seems to be a pretty good estimator for the mean of the population. Seems to go well. But if you want to estimate, okay, the sigma square from the population variance, it turns out there is another one that is actually good. Well, pretty good. Is y minus y bar, the whole thing square, you sum them up. But instead of divided by n, you have to divide it by n minus 1. You remember this one? Yeah, all right. So the reason that y is n minus 1 instead of n has to be done with the type of estimator. That's we probably gonna have to, talk about this next time. I mean, next video. But for now, let's take it this way: that the good estimator, not yi minus y bar the whole thing square, add together, divided by n. No, you have to divide it by n minus 1. All right, and that's because of the distribution. It turns out with the distribution of this, you kind of know now that it's going to be chi-square, John. But because you only take the degree of freedom down by 1 instead of n, you take n minus 1. So it's going to be the distribution of the chi-square with the different degree of freedom. It's n minus 1 degree of freedom. This is the estimator that can be used to estimate the population variance, a better one than divided by n. All right. So I think this is something that, you can, at least if you take this result and apply it, then the rest is just going to be pretty much the same, because now we know how the populations and the sample are linked together. Then you use the same trick one more time, right? The only thing that's gonna sort of like leave like a question mark at this point is we have to use the n minus 1. That's what it is. All right, and we haven't proved this one yet, but we're gonna, not so sure if we have a chance to do this. But if you take this, then the rest is gonna be easy, because instead of normal, well, don't talk about instead, but in this case, what you have to refer to is the chi-square distribution. All right, so let's take a look at this example. All right, so go back to that same bottling machine. All right, and because let's say that assume that they have the normal distribution of 1, and suppose that we plan to select a random sample of 10. Okay, we assume that we're going to do 10 bottle. So that's your sample size. The number of sample is 10. If these 10 observations going to be used to calculate the S square, okay, so that means you're trying to estimate, somehow the population variance. It might be useful to specify an interval of values that will include S squared with the high probability. See? So the textbook is trying to lead you to the way that every time that you want to use some statistics value, it's not going to be precise. It's going to come up with the range. Okay? And that lead you to give you an idea of like how much or what is going to be the level of confidence that you can use this number. Okay, so that's why it's coming as a probability within the range. So the way that they ask is this. So they say, hey, if these 10 observations are used to calculate the S square, it might be useful to specify an interval instead. Not only use the value, but let's say, hey, it's going to fall within an interval. That will include the S square with a high probability. Find that number such that the probability is 90%. So what you're trying to find is you're trying to find those two values. Oh, my battery is gone. All right. Never happened before. Sorry. All right, but anyway, I'll keep talking. All right. So what we have over here is what you trying to get to is you want to figure out the two numbers, okay, that eventually the probability of S square between these two numbers give you the probability of 90%, 0.9. Okay, cool. All right, and now because you know that the S square is the sample variance, right? But then for you to estimate the population variance, you know that it's going to distribute with this good estimator over here. So you're trying pretty much to, how can I say it? You're trying to go back to the chi-square distribution. That's what you're trying to get to. All right. Means here just want to confirm this relationship one more time, right? Look at this. Because you already started out from here, okay, here, right there, okay, and you already knew the behavior of this summation on the right hand side, okay, and if you divide through by the sigma square, everything will go back to this chi-square with n degree of freedom, right? On and on, right? So that's what we did last time, previously. So what you can do is I just move n minus 1 to the left hand side, okay, and divide through by the sigma square. And that's why this theorem is trying to say, okay, let me highlight this one. Maybe I didn't highlight this in the at the time that I mentioned about theorem 7.3. So this is what it is. So the n minus 1 s square over sigma square over here will representing this one right here, right? Okay, it's the summation of yi minus y bar, the whole thing square divided by sigma square. But then we already knew that if you talk about this, this will be chi-square distribution with the n minus 1 degree of freedom. So that's why I am after this dude over here. Because I know the behavior of this n minus 1 s square over sigma square is going to have an chi-square distribution with n minus 1 degree of freedom. With me, guys? All right, so that means you already got the s square, okay, so over here. So that's what you set up for. You want the s square, all right, to be within the two numbers that you want to figure out. But those two numbers give you the probability of 0.9. What are the two numbers? You don't know for sure what is s squared is going to distribute it, but you know what is going to happen with the n minus 1 s squared over sigma squared. So I manipulate this by multiply by the n minus 1, divide through by the sigma square. See this? All right, so once I do this, I know this is going to be my chi-square with the n minus 1 degree of freedom. And in this case, because you do 10 bottle, so your degree of freedom is going to be n minus 1. It's going to be 9. Nice. Okay. And from the information given, the sigma square is 1. So that's it. So what you have, when I say that's it, means what you want is you want to figure out the two numbers on the left and on the right. But now the two numbers are changed a little bit. It's not B1 and B2 anymore because that was related to the s square. Now you want this number right here. You can call this A1. That's A1. And another number over here, you call it the A2 right here. Okay. And now you can look it up in the table again, which is going to be the chi-square table. But then, well, to be fair, well, you want the probability to be 0.9. You can split half-half. Right? When it says split half-half, mean, all right, but Ajahn, I can have like, because I want the interval above and below, so I can split 0.05 to the upper side and split another 0.05 to the left side. So that means I have two cuts off over here. With me? All right, and those are the two values that I want to figure out. And that will give me A1 and A2. Nice? All right, so over here now, you can look it up in the table now. Because now, what you have here is, once again, the cutoff area is 0.05. From the chi-square table, the area on the left, this whole area over here that I'm highlighting blue over here, is going to be the same value again, 0.95. So that's why I look up on the table with chi-square of 0.95. Cool? All right. Oh, I'm sorry. I'm talking about, wait. This is 0.95 is going to be on the left. Sorry, guys. Am I right here? Yeah, sorry. I'm doing in reverse. My bad. I'm starting from the A1 first. Sorry. Okay, do it one more time. So right here. Sorry. Here. Here we go. There you go. Okay, so if I want to figure out the A1, so the area that I say the cutoff an area of 0.05 on the left will leave you with, okay, bear with me a little bit, guys, almost done. the area on the right, which is the alpha of mine. Here we go, here we go. The one that I'm highlighting over here. This area is going to be 0.95. The big area, the one in orange. That's why I have to look up the chi-square of 0.95 at the degree of freedom of 9. So intersection is this one right here. That will give me the A1. With me, guys? All right. A1 is right here. And now I do the same thing on the A2. Let me use another color here. So the A2, I have 0.05, which is the area in green over here. So, and that will leave me with the, I don't know you get me or not, but here, the area on the left is now 0.95, but the alpha is 0.05. Cool? All right, so I hope you kind of like understand it's a different value of alpha. At A1, alpha is 0.95. At A2, the alpha is 0.05. At A1, alpha is 0.95. So I hope this helps. All right, so for figuring out A2, I just look up the table of chi-square at 0.05 at degree of freedom of 9. So I get this to be my A2 right there. All right, so that's it. So when I have this A1 of 3.325, I can plug it back in and reverse, try to calculate the B1 in the previous page. Cool? Because A1 is just this, and this one just link you back to B. So that's all I have to reverse to. Same thing happens to the A2 of 16.91. Okay, plug it back in there and recalculate back the B2. And that's how I can tell that what should be the value of B1 and B2. That is not guarantee. I keep saying guarantee. Sorry. That will give you a 90% confidence with the probability of 0.9 that it will include its square in there. All right. So I hope this helped. Okay. All right. So now for the rest of this one, I hope you don't have to worry about it, but I hope you see the connections. For example, let Z be a standard normal. And let's say you have W, which is chi-square, with some degree of freedom given. Then you might want to build another random variable T, which turns out to be the ratio between Z and the square root of the W divided by the degree of freedom. See, now things get more complicated because now you build another function, which is Z divided by square root W over nu. And this is, well, it's not that bad because it has a name for it. It's called the T distribution. But then you don't want to deal with the distribution like this anymore because it's now too complicated. But I hope you see the connections. See, you start with the Z with one type of distribution. You have now another W, another type of distribution. You combine it into another variable T. What will be the distribution of this? See? All right, and it turns out you creating another type of distribution is called T distribution. And this is how it look. All right, we're not going to try to do this. I mean, I know it's start to get crazy. But at least this is the one that sort of like build on top and on top and on top of each other. You start from the normal, get to the Z square, you get to the chi-square. Now you combine the normal and the chi-square, take the ratio. After the square root, you have another T distribution. On and on and on. All right. So don't worry about the T distribution. Well, this is really bad. Okay. I can say it. Well, if I keep doing this, the thing's going to get bad in the sense that you just have to look it up on the table. That's all. I mean, the complication is in the not being familiar with the distribution, but not the understanding of it. So I think you just concentrate on the normal distribution and the chi-square distribution. I think that's more than good enough. All right, cool. All right, but I hope, I don't know my explanation works or not, but if you can dig a little bit deeper into this handout, I can even have you look at the ratio. See this? You can even build the ratio between S1 and S2, which is the variance of the sample 1 and the sample 2. And this will give you another type of distribution. We call it an F distribution, which come from two chi-square distribution and come in the proportion or the ratio between the two. See? Love it. All right. So that, I think, conclude this lecture right here. All you have to concentrate on is just understanding the normal distributions, a little bit of chi-square distribution. I think just a little bit. I think that's good enough. But I tend to just going to ask you for the normal distribution because that's the one that you're familiar with the most. Sounds good? All right, guys. Sorry for the disappearance of the camera. I mean, the battery is just exhausted. So, all right, it couldn't keep up with the whole thing. But anyway, it's done for this video. I hope you learned something and see you in the next video. Bye bye.